So in this video, we're going to introduce the concept of a standard reduction potential, which is abbreviated as E naught. We now know that naught always means in standard conditions. And talk about how that influences how to calculate voltages and make batteries and whatnot. So first, just a little review. Here is an equation where we have zinc solid in a solution of copper sulfate. And when they react, they form zinc sulfate and solid copper. Okay. So first thing, a little bit of review, is we want to figure out what is getting oxidized, what is getting reduced, or if that's happening at all. So oxidation number for zinc is 0 here because it's a solid. In this case, I know that sulfate is -2, so zinc must be +2. So zinc is going from 0 to +2. On the other hand, copper, here, sulfate is -2, copper, it must then be +2, is going from +2 to 0. So since copper's charge is dropping, copper is getting reduced. Since zinc's charge is increasing, it must be getting oxidized. It must be losing electrons. So what this means is zinc is losing 2 electrons. And where are those electrons going? They're going to the atom of copper. Now, electrons, we know, have a negative charge. So what can we do with those electrons? Well, if we can separate electrons from the atoms, we can turn the flow of electrons, or the transfer, into electricity. And that's exactly what a battery does. It harnesses the power of this electron transfer to form a battery. And the most common batteries that we're going to talk about in this class are also called galvanic cells. So it's pronounced a galvanic cell. Fancy word for saying a battery. And this is what they look like, kind of zoomed in, if we cut one open and actually figured out what was going on the inside. There's a lot of information going on here. Okay? First, this connects back to our old equation, where we had zinc solid plus copper sulfate forming zinc sulfate plus copper. So we have the zinc metal right here. Okay? That's our zinc sulfate. Okay? Or excuse me, our zinc, floating around in a solution of zinc sulfate. That's right here. On the other side, we have our metal piece of copper right here, and our solution of copper sulfate right here. So those are the 4 things that are set up. You'll notice the way this is drawn is that electrons are leaving this piece of zinc and they are flowing through this wire into the copper. How do we know that that's the transfer, the direction of the electron flow? Well, we said here that zinc was getting oxidized. Okay? And we know oxidation is loss of electrons. So the zinc metal, solid zinc, is going to lose electrons. So what we can see here is those electrons are being lost. We're attaching this to a wire, so the electrons are going to flow through the wire until they get added to the copper. Okay? There's a vocab term for the compound, or the half of the cell, the galvanic cell, that's getting oxidized. And that is called the anode. A-N-O-D-E, anode. Okay? So the anode is where oxidation occurs. The way that I like to remember it is anode and oxidation both begin with vowels. But you can also remember that anions and are negatively charged and anodes are where oxidation is happening. They both begin with A's, if that helps you. Either way, it's a vocab word to know. On the other hand, there's a term for the substance, the half of the cell where the electrons are being gained, that's getting reduced. And that is called the cathode. So the cathode is where reduction occurs. Okay? Whereas the anode is where oxidation occurs. There's two other things that we need to notice. Here, we can plug in something that needs electricity, in this case, a light bulb. The flow of electrons can run through this light bulb here, power it, and keep going on and on. We could also plug in a voltmeter to measure the voltage. And that's what we're going to talk about next, and that's what's important in a battery. Like if you have a 9-volt battery, 9V, that equals 9 volts. It's because it's measured based on the half reactions to create a potential of 9 volts. And we'll talk about that in a second. But the last thing you need to think about is here. If electrons are constantly being lost from this zinc metal, then that means over time you're getting more and more electrons on this side. So this side is going to become negatively charged, and this half of the cell is going to become positively charged. Ooh, batteries, positive and negative. However, we don't want that charge to build up over time. So the last thing that you need to know about galvanic cells is this piece right here in the middle. Okay? This is called a salt bridge. So a salt bridge is just an ionic compound, usually that's soaked in some type of paper. And what that allows is for the electrons to continue to flow in a circuit, constantly in the same direction, but over and over so that charge does not build up. So again, what you need to know about a salt bridge, it's made of an ionic compound, in this case Na2SO4, and the purpose of it is to prevent charge from building up. So, overview of galvanic cells. I was mentioning earlier how we could connect a voltmeter to a galvanic cell to measure the voltage. And when we do that, we would be measuring something called the standard reduction potential, which is abbreviated as E0. Standard conditions are 1 molar concentration at a pressure of 1 atmosphere. And these are voltages that measure the electric potential. Okay? This is essentially the electric potential of a half cell. So something that's getting reduced. How many electrons essentially are flowing and what kind of voltage and then current can we make? So this data is often given in standard reduction tables, like the tables for entropies and enthalpies. And one thing to note, they're always written as reductions. And this is just to avoid any confusion amongst numbers. They're always written as reductions. How do I know that these are all reduction equations? Well, if we look at each one half reaction, where are the electrons? The electrons are on the reactant side. So electrons are gained. And if electrons are gained, that makes it reduction. So when you have fluorine gas gaining 2 electrons to become 2F minus, that has a voltage potential of 2.87 V, which is volts, a measure of electrical potential. These tables are usually written with the most greatest electron reduction potential first, and as you go down, it decreases. So I put a gap here for a particular reason. There's a ton more compounds in this table. Notice hydrogen is our standard. We set hydrogen as 0. Okay? H is 0. So a half cell, scientists decided when hydrogen is a half cell, the voltage of that is 0. Everything compared to that will either be positive or negative. Okay. How do we use this information if we want to construct a battery? Well, how do we calculate the standard reduction potential of a cell? The goal is to make the most positive E0. Okay? So the equation that you need to know, the potential of a cell depends on the 2 half reactions. Because if you remember here, we don't just have one reaction happening. There's one reaction happening on this side and another reaction happening on this side. One thing is getting oxidized, zinc, one is getting reduced, copper. So we need 2 half reactions. Each one is going to have its own standard reduction potential. So if we take the reduction potential of the substance that's getting reduced and we subtract the reduction potential of the substance that's getting oxidized, that gives us the standard reduction potential for the cell. So again, this is of what's getting reduced, and this is of what's oxidized. So how do we use that? Well, here's an example problem. Given the reduction potentials in the table above, what is the standard reduction potential of a galvanic cell with these half reactions? So, to calculate the standard reduction potential, it's E naught cell is equal to E naught of what's getting reduced minus E naught of what's getting oxidized. So our goal, remember, is to make the greatest positive E naught cell. So, when these two numbers are brought together, okay, I can either have the iodine getting reduced and the zirconium getting oxidized, or I could have it backwards. So let's just do one of them first. Okay? So let's say that the iodine is getting reduced. We'll call this our reduction first. Okay? So the cell, the voltage of this cell is 0.54. So E naught of the whole thing will be 0.54 minus what's getting oxidized, which is the other half reaction. Now, here's where the trickiness comes in. One thing to watch out for. Since this is a reduction, because electrons are being gained, if I make it the thing that's getting oxidized, I need to flip the reaction. And if I flip the reaction, that makes this voltage become positive 1.53. So I would have 0.54 minus positive 1.53. And if I go ahead and figure out the overall cell voltage right there, I get negative 0.99 volts. Negative standard electron potential. Negative standard electron potentials, not spontaneous. So electrons would not flow in this direction. Iodine can't be getting reduced. Zirconium can't be getting oxidized. So therefore, if we look at the other way, Z cell equals E naught of what's getting reduced minus E naught of what's getting oxidized. Okay. In this case, let's make the zirconium the stuff that's getting reduced. So I'll have 1.53 minus, since the iodine now needs to be getting oxidized, I'm going to flip this to make it negative 0.54. And now if I go ahead and do the math there, if I add these numbers up, I get 2.07 volts. So this would be the voltage formed with these two half reactions. A battery with a voltage of 2.707. This is a spontaneous direction. Let's do one more together. What is the standard reduction potential for the reaction below? So now we're given a reaction. So first I need to figure out what's getting oxidized and what's getting reduced. Because the equation is E naught cell is equal to whatever is getting reduced minus what's getting oxidized. So tin, Sn is going from +2 to 0. Nickel is going from 0 to +2. So tin, therefore, is getting reduced. Nickel must be getting oxidized. So if I plug this in, okay, E naught of the cell is going to be the voltage of what's getting reduced, which in this case was Sn2 plus, negative 0.14, minus the voltage of what's getting oxidized, in this case nickel, negative 0.25. So if those numbers are added together, I'm going to get 0.11 volts. So this is a spontaneous cell. This would have a voltage. It would produce electricity, but nowhere near as much electricity as this combination of half reactions here. So you need to understand how to calculate E naught of cells given half reactions using this equation, standard reduction potentials, all the vocabulary here, and we'll be good to go.